something else. You make one change in the function, the output hash changes dramatically. Okay. And that is why we can use it to test whether a input file has been manipulated if I give you something else. Similarly, you can take a JPEG file and give a hash of it. Anything which is a digital string can be converted into something another number. So, this is the SHA-256 hash forms the first stepping stone into our world of cryptography here. Now, this gives us the first clue on how to detect a tampered message. If I have sent you a message or I have given a text document and in the meantime somebody has changed it, the hash numbers will change. Okay. So, you can always check the hash of the document that you received and check it against the original hash, okay, and you will know whether a document has been given to you in an unmodified state or in a modified state. It is very important. As we move forward into crypto contracts, this will become very useful. Okay. Now, hashing is an irreversible process. It goes from input to output. Okay. But sometimes we need the reverse also. From the output, I need to generate the input. Okay. That is called encryption. And the basics of encryption is like this. You have the original text string. As I said, a text represents an image or anything which can be represented as a set of digital numbers, and to it you add a secret key, which is another text string. Some people call it a password or whatever you want to call it. It is another secret string, and then you push it through the encryption function, not SHA-256 as yet, but some other function, and out comes an unreadable message in ciphertext. So, then the transformation happens, the input goes into output, and there is a secret key which is used to encrypt it also. Now, the nice thing is that this unreadable message can be decrypted with a corresponding negative function, reverse function. So, given the encrypted message, you can decrypt it and get the original message back, provided you have the secret key. Okay. Sounds good? Not quite. Okay. Now, let us see what happens. If I have to send you a piece of information, for example, A will meet B at 2 p.m. at V, at a place called V, and I can encrypt it with a secret password and I send it across to you. Now, the trouble is, and this is a fundamental problem of encryption, how do you send the key? Because to decrypt the message, you need the key. How can I send the key to you? Because if I am sending the key to you, if somebody intercepts the key, then the message is again blown. So, this has been the challenge of cryptography since thousands of years. Okay? Now, and there was really no solution to this. People tried various things. For example, your bank sends you the encrypted document in mail, but sends you the password in an SMS. Now, that is fine at our level, not at a higher level. Okay? I mean, anybody who can intercept your mail can also intercept your SMS. So, this is a challenge, and this challenge was overcome, I mean, about 50 years or 30 years ago through a process called asymmetric encryption and decryption. Okay? And this forms the basis of all of today's cryptographic exchange of messages. In this case, we have two keys, call it K2 and K1. Okay? A key is nothing but a string of alphanumeric string, K2 and K1. So, if you encrypt the clear text with one key, you cannot decrypt it with the same key. So, if you encrypt it with K2, it has to be decrypted with K1. And it is symmetric in the sense, if you decrypt it with K1, you can encrypt it with K1, the other way around. You can see the diagram out here. So, K2 encrypt ciphertext. If you try to decrypt it with K2, it will fail. You need K1 to decrypt it. Now, this fundamental property, okay, of encryption algorithm has given rise to the most powerful ways of communicating messages today. So what happens is this, if I have to send you an encrypted document, I will first go to you and pick up your public key. So now this K2 and K1 are replaced by the words public key and private key. So if I am sending something to you, I will go to your website and I will ask you to please send me your public key, and you can send it to me in the clear, you can send it to me, you can have it posted on your website as an email footer. It is public, it is known to everybody. Now I can encrypt the message with your public key. Only you can decrypt it because you have the private key. Having the public key is of no use. Even though I have encrypted with the public key, it cannot be decrypted with the public key. It has to be decrypted with your private key, which never leaves your secure machine. So now I have a perfect way of ensuring that a message goes across secretly to you without compromising on the key distribution process. Okay? This is one important. But there is another side to this story, another side. So here we have ensured privacy, fine, privacy is guaranteed. The other is authentication. Authentication means you have sent me a document. I have received a document which claims to have come from you. How do I know it has come from you? Okay? I don't know. Anybody could have said that, I am sending this document on his behalf. So this part is like this. So what they do is, the public key is encrypted with the private key, and that creates what is known as a signature file. Okay. So what I will do is, after I have got your signature file, I will use your public key to unlock it, and if after unlocking it I get the same public key, then I know it has come from you, because only you could have encrypted it with your private key, no one else could have. So if I am sending a key and saying this belongs to Govindarajan, then it will not be possible, because only I can use only Govindarajan can use Govindarajan's public key to send the document, and I can only decrypt to see whether it works. So now you see this asymmetric encryption mechanism gives us two benefits, simultaneous benefits. One is privacy and the other is authentication. These are the two very interesting things which come out of this algorithm, which was first created by this RSA people. I mean, the Rijik, Shamir, and I forget his third fellow's name, they did it. And this has made cryptography so very powerful today. The only way of breaking this as of now is either extreme brute force, which the CIA can afford, or possibly by quantum computing. Modern technology as we have it today does not have the capability of breaking this algorithm at the moment, okay? Except by brute force, trial and error, that's a different matter, or by holding a gun on somebody's head, kido. That's much easier sometimes. You blackmail somebody and get the key out. People forget that. Social attacks are more dangerous than technical attacks. Okay. So now we have this beautiful mechanism, and which allows us to create what is known as trustless contracts. How to create contracts where nobody trusts anybody else is very important. Okay. How to create trustless contracts. So let us see. There is somebody called B who is transferring a asset, I am calling it a house, to a person called C. Okay. Now B claims that A transferred the asset to B at some point in time, and so she has a clear title to transfer it to C. Okay. This is how you will see any conveyance contracts are made. If you look at any, if you buy a house, you will see that this land belonged to somebody, which was given to somebody, which was bought by somebody, and hence I am giving it to somebody. This is how all asset contracts are made. Okay. Now, so what I have to do is, I have to somehow produce the original contract which showed that I got the land from A to B, and hence I am B transferring the land from B to C. This is the structure of any contract. Let us see how crypto functions can bring in this kind of logic. Okay. So, A creates a contract called C1 transferring H25 to B. Okay. So, how does a contract look like? A contract looks like a string of text. The first part of the string contains the public key of A, followed by the asset description, okay, followed by the public key of B, which means it is a public key to public key transaction. Nobody knows who is A, B or C. It is A's public key transferring to B's public key. So, it is a pay to public key kind of a contract. Okay. Now, A has to add his signature to show that he is doing it. So, he takes his own public key, uses his private key to create the signature, appends it, the string becomes longer. All those green blocks are actually strings of characters. Okay. Then what he does is, he creates a hash function to authenticate that nobody is changing anything inside and creates the another string in front of it. So, this long string consisting of the 256 hash, the sig A, the KPUA, H25 and KPUB constitutes a digital contract, okay, which shows that something has got transferred from A to B. Let us see, we do not believe anybody as yet. So, B creates an identical contract when he is transferring it to C. Okay. Now, C does not trust B. So, to him the entire